Hi everybody, hi, Mike here. Here we're going to continue our discussion of electron configurations. If you go back to part 3 last time, you see we left off on iron. And one thing I forgot to mention, iron is what? Paramagnetic? Diamagnetic? It is very paramagnetic. And that is because it has not only just one electron or more with unpaired spin, but like 4. Now, I want to distinguish two things. Today's going to be about me trying to avoid panic. There is another term called ferromagnetic. And as you can tell by the name, that's based off of iron. So the best thing I can say is that there are some elements that are paramagnetic, and at the macro level, they won't align themselves with a magnetic field, and that has to do with their crystal structure. So iron, for example, if you bring it next to a magnet, if you take a magnet and you rub it on a piece of steel, it will become magnetized because of the content of iron. There are some elements that are paramagnetic but not ferromagnetic. So even though they have a net magnetic field, their sort of structure of the crystals won't let them align with that magnetic field. So this is something you can't quite predict from the electron configuration, but this is something you can, as well as diamagnetic. So I just wanted to clear that up. Iron's highly paramagnetic. It's also ferromagnetic. So, my expectations of you are to be able to determine if you can differentiate between para and diamagnetic. All right. Now, what we're going to talk about next, more of me sort of trying to stave off any panic. There are some weird electron configurations. It's probably not a surprise to you, that they occur in the transition metals. And this is because you've got two patterns, two rules of electrons filling orbitals that conflict each other. This is where Hund's rule starts to conflict the whole electrons want to go to the lowest energy possible rule. So I'm going to show you the weird one that I can explain, and I'm going to show you two weird ones that I can't explain, starting with chromium. Okay, I've got to start it on chromium. Chromium has 24 electrons. It's a fairly close neighbor to iron. And I've even gotten the electron configuration started in the noble gas form. This is everything up to argon with 18 electrons. All right? So, let's go ahead and throw the 19th electron in there. And this is where it gets weird. And the whole point is, folks, you're not going to have to worry about weird. There's exceptions to patterns. And actually, I can explain this one. That's the 19th electron. Where's the 20th going to go? Well, you'd say it would go there because it takes less energy for it to do that and then it can remain unpaired. Well, that's not actually true. So with chromium, you're going to find out that those next remaining 5 electrons go there like that. And so technically, you got something where it takes less energy because these two orbitals are so close in energy that it actually, that other electron would go up here because they're very close, closer than the energy of pairing. So this would be argon, 4s1, 3d5. All right? So that's just a little weird thing. Manganese, that 25th electron, it's instead of going higher, and actually I can explain this pretty good, it's going to want to go there. All right, so that would be manganese. Now, where I can explain what happens next is copper. Copper, what you're going to have happen is, for some weird reason that I can't explain using the things we've talked about, copper will have 10 electrons go in here and be of all paired spin, and then 1 down here will be of unpaired spin. You'd say, well, why wouldn't the one, they pair here and then have one of these unpaired? I don't know. Nature doesn't like that for some reason. Okay, let's talk about the ends of the periodic table where they obey the octet rule. Once again, let's review the octet rule now in its new form. An atom or ion is most stable when it has the same electron configuration as a noble gas atom. Okay, let's talk about that. Guys, I want to update you on my garden. Look at, never have I been so happy to see that guy. That right there. That's asparagus. Here's my turnips. So I'm starting to feel a little bit better about the world now that I can sort of not depend on anybody. Okay, let's go back and talk about more electron configurations. Okay, so now we're going to talk about something called isolectronic series. Those are the things that all have the same electron configuration. Okay, so let's take 2 electrons. That's a point where well, let's talk about what obeys the octet rule. What obeys the octet rule are all the noble gases. That would be helium. Helium has the electron configuration 1s2. All right? But so does lithium. In its stable form, lithium plus. Lithium has 3 electrons. And if you take away an electron, that's still got 2 electrons. And what I'm trying to show here is that no matter what the nucleus of an atom is, the electrons still have the same tendency to want to fill or unfill a shell. So these all have the same electron configuration, 1s2, same as helium. And as a matter of fact, if you went over to hydrogen, one stable ion, certainly more stable than a single hydrogen atom, would be the hydride ion. All right, so those are all things that have the same electron configuration, and they're much more stable, except of course in the case of helium, than the original atom that they came from. Let's go to the next shell, 1s2. Excuse me, quantum level number 2. This is the electron configuration 1s2, 2s2, 2p6. And so let's pick out the noble gas atom that has that electron configuration. Would be neon. However, if you go over to sodium, back when we first started our journey here together, we talked about the fact that the stable form of sodium is Na+, right? And the stable form of magnesium is Mg2+. So you folks all know that those all have 10 electrons, and now you're kind of getting an idea why. It's all based on the electron configuration. For some strange, mysterious reason, nature wants a filled shell. Aluminum 3+, throw that in there. All right, let's go nonmetals. Fluoride ion. All right, oxide ion. All right, nitride ion. All of these have the same electron configuration, 1s2, 2s2, 2p6. So I got something for you to do next time. I want you to write the series of atoms or ions which occur and are stable at 18 electrons. I want you to write as many atoms or ions as you can which obey the octet rule. And well, I'm not going to tell you what noble gas that is. You guys will explore that on your own. Hang in there. More tomorrow. Take care of yourselves. And scene.